This video derives H star, the optimal hedging ratio that we've been using throughout chapter 5. And when I present this in class, I typically say, look, H is nothing but the rho times the standard, which is correlation between the spot and the futures, times the standard deviation of the spot price, the change in the spot price. You think of it as change in the price each day, divided by the standard deviation of the futures price changes each day. And I said with a naive hedge, this would equal 1, and I rationalized it by saying, look, with a naive hedge, you're assuming that, first of all, that the spot and the futures are moving perfectly in sync with each other. They have the same variance, the same volatility. So therefore, the ratio of these two numbers is equal to 1. And we're assuming that the perfectly positively correlated it's 1. So the hedge ratio using naive hedging is plain old 1 in this case, assume. But I said, what happens when there's basis risk involved? And that's due to delivery options and cross-hedging issues that we talk about in class. And when you have basis risk from whatever sort, the cross-hedging or the delivery options, you're not going to have a perfect, it's not the difference between this, remember basis is equal to the spot minus the futures, it's not going to be constant. It's going to change. So it could look like this, right? In which case the basis is changing. And there could be cases where the two just don't match up in terms of volatility. So you could have something that's much more volatile, fairly correlated, but much more volatile. So we need to reflect in an optimal hedge ratio, where what I'm saying is an optimal hedge ratio is trying to reduce the cash variation, the cash flow variation in hedging as much as possible. And as much as possible means it depends on the correlation coefficient as how much you can eliminate it. So what I said in class was, and I didn't derive it, I basically reasoned it out to say, look, you need to know what the correlation coefficient is, you need to know what the sigma of the spot is, and the sigma of the change in the futures price. And if you have, for example, if you have a spot price that's highly volatile and the futures price is much less volatile, then what happens is this number is going to be substantially larger than this number, which means all else being equal, it's going to drive up your hedge ratio. You're going to need more futures contracts, really what the hedge ratio is saying. The higher H goes, it's telling you that you need more futures contracts to absorb this extra volatility in the spot. And it also depends on how highly correlated and the correlation between the two. If you have correlation that's perfect positive correlation, may look like this, as best I can draw it, then the higher the correlation, the more futures contracts that you're going to need, because the futures contracts are going to be very successful in offsetting this risk. So you go long the spot and you're going to short the futures contract. The net effect will be when you go long the spot and then you short the futures contract, then the two are going to net out and you're going to have zero variation in your cash flow. It'll be a constant, this line. Okay? Now, if you have zero correlation, it's really hard to draw zero correlation, but what zero correlation means is you should not be hedging. If this is 0, for example, it means you're taking a spot and you're using a futures contract that's uncorrelated, independent, statistically and economically unrelated to the underlying spot, and using that to hedge. What you're going to actually do is you're going to actually add risk to your situation. If you have corn and you try to use lumber or orange juice futures contracts to hedge that, they're probably going to be completely independent, and so you're going to have a position in corn and you're going to have a position in orange juice or lumber that are going to basically add. There won't be any netting effects going on there. So that's how I explained it in class. But what I want to do in this derivation is to derive it more formally. And the way we derive it more formally is we take a position. We look at assume that a buyer, you have a trader. Let's say a trader has a commitment to buy the spot at some point in time. So it'll be at expiration for the futures contract in this horizon that we're looking at. We're going to buy the spot, and the spot price will be ST. Okay, so we have a commitment, and what we want to do is we want to hedge that position. And when you hedge a long position, as we have a commitment to buy, you want to have a short position. So we're going to hedge it with a short position, and so the cash outflow, so we're going to measure cash outflow in this situation, is going to be QST. That's the cash outflow associated with the spot itself. You're going to have to buy Q of the spot at expiration. So it could be, it could be if you had Q as 1, and 1 bushel times whatever the spot price of corn will be at expiration. Okay. Now let's look at the futures position tacked onto this. So the futures position will look like this, as explained in your text. And I'm following page 106 and 107 of your text carefully, because the text, like I've said before, does quite a good job in explaining this. It gets right at the heart of the situation. So notice that we took a short position. This says, believe it or not, this says we took a short position in a futures contract. Now, how do you know that? Well, this is H is the hedge, the short position. This is the futures price at expiration. Okay, right? And this price is the futures price we locked into. So if you unravel this math, it's HFT plus HF. This is the cash flow from going short the futures contract, because when you go short the futures contract, you're going to collect this cash, right? And you're going to give up the underlying commodity. Okay? What is the value of the underlying commodity that you're giving up? It is worth HF capital T. Okay? So now, let's go back to this part of the equation. Okay. Now let's do a math trick that shows up a lot in higher level finance. And and the reason we do it is because it allows for a much neater solution. And so we're going to take we're going to add and subtract. We're going to add and subtract QS to this equation right here. So it's going to be QST plus QS minus QS minus HFT minus F. So same thing. You add, subtract, doesn't do anything to the formula. Just makes it a little uglier, but it'll boil down to something nice. Now let's collect the S's and the F's. So we can collect the S's here and here, and we can collect the F's already collected. And so we can say QST minus the spot HFT minus F plus QS. And so here we have nothing but the changes in the spot over the horizon, over the hedging horizon, the change in the futures price over the hedging horizon. Okay? Simply relabel this delta S. We'll put a little S here, a little subscript. And this is delta F. Okay? So when we do that, we get Q delta S minus H delta F plus QS. Okay. Now, let H equal the ratio of the hedge to the underlying spot position. So this is the size of the hedge, and so you can think of this as the number of futures, the total number of futures position relative to the size of the inventory that you're hedging. And with a naive hedge, you can think of this as one bushel to hedge one spot in your inventory. That's with a naive hedge. Okay, let's get rid of that. Okay, so when we do this math, we're left with Q delta S minus H delta F plus QS. Okay. Now, what we want to do is, now is calculate the variance of this. What is the variance? How wiggly is this whole set of terms over time? How wiggly is that? And so that's what the variance is going to capture. Okay, so writing that out here, it's going to be the variance of Q delta S minus H delta F plus QS. Okay, now keep in mind that this guy is constant. This is a constant. It's going to have a variation of 0. Why is it a constant? Because this is the price of the spot at the day you entered into the futures position. This is the quantity. It's not going to change over time. You have inventory of this amount, and this is the value of it. It's unchanged the day you put it you get into the futures position. So you can ignore that. And so really what we want to do is we want to calculate the variance of this guy. Okay? And don't forget, this is also a constant. And when you calculate variances, remember, if you want to calculate the variance of x, how wiggly is x? You take x minus the mean, okay, squared, sum them up, sum the deviations. Why do you have to square them? Because if you didn't square them, they would add up to 0. Because you take the mean right down the middle, the sum of these deviations would add up to 0. You'd go nowhere. And basically, you're taking an average of those. Think of it that way. Okay. Now, so that's where the square terms comes into play. And as I've said in footnotes to my footnotes to my own personal notes that I give you, when you have when you want to calculate the variance of AX, where A is a constant, what you're doing is you're calculating the sum of AX minus AX bar squared divided by N, which equals A squared sigma X. So that's an X there. What's happening is it's simply A squared times the variance of X itself, because you're multiplying it by A. So what this means is, what ultimately all this means is that you can bring Q squared outside of what we want to do. Now I want to calculate now the variance of what's in the middle here. Okay, I want to calculate the variance of this. And so the variance of a difference is going to equal the variance of delta S, the variance of the spot, plus H squared times the variance of the change in the futures price minus how the two things covary, 2H covariance between delta S and delta F. So you're really looking at, really what you're looking at here is you're looking at, look, I got this variable is wiggling around like this, call it delta S. I have a futures contract that's wiggling around delta F, and if I was to subtract these two things, I have to consider how wiggly, how volatile S is. I have to consider how volatile delta F is, and also keep in mind I don't have a full delta F. It's based on H, how much H I have there, the hedge ratio, which is a constant. And then I have to subtract out how these two things covary relative to each other, and that's this term right here. How do the two covary? So it's possible that if you had two, series here, one that moves like this and another that moves like this, that if you add these two together, the volatility of the first one, the volatility of the second one, and you subtract the covariance, that when you actually get that too, you basically come up with a flat line, which means you can make this whole thing right here 0. You can turn this whole thing into 0, provided that the correlation, which is buried in the covariance, is positive 1, and I'll explain that shortly. Okay. Now, what we want to do is we want to find the slope. We want to find the slope. Let me rewrite it here. Oops. We want to find the slope of this so that it gets as close. We want to get as low as the slope. We want to get the cash flow variation as low as possible, and when we do that, we'll end up with a slope of 0. And what I'm saying is this: you have cash flow variation. Here is your optimal hedge ratio, okay, on this axis, H star, and here is your cash flow variation, which is what I'm trying to calculate right here in this formula. And so if you're unhedged and H is 0, let's say you start out right here, you can get rid of, if you have the right correlation coefficient, you can get rid of all of your cash flow variation if you have the right number of futures contracts, H star. And what that means is, here, look, the cash flow variation is 0. It's a constant when you get here. Notice what the slope of that point is. It's a slope of 0 at that flat spot. And that corresponds to this term in here being 0. Okay? Now, you may not always get it to be 0, this big term. You may not always get it down to 0 here. This is only going to happen if you have perfect correlation, positive 1,0. And you could also get it if you had perfect negative correlation. Okay. Now, if you have correlation that's not perfect, what will happen is you will have hedge ratios that are a little lower, and not only that, you'll have hedge ratios that will be somewhat lower in this direction, and you won't be able to get rid of as much of the variation. So it might look like this for some, maybe row of, let's say, 0.7. Okay, and if you had a row, of something very low correlation, it would look like this and shoot right up. And so what's happening is, if you have the right hedge ratio, the optimal hedge ratio, given the correlation coefficient, this correlation here would be correlations, let's say it's 0.10. We're looking for this flat spot, slope of 0. We're looking for that slope of 0. And your hedge ratio will drop, your optimal hedge ratio will drop depending on the correlation coefficient. So you're going to have the highest hedge ratio when your correlation rho is equal to positive 1 or negative 1. Okay. Now, if you don't find that optimal hedge ratio, you can actually take on more risk than if you didn't hedge. If you didn't hedge, you'd be right here. But what this is telling you is if you're going up above this line, that means that you over-hedged in a sense, and you're actually taking on more risk than you should by hedging. It doesn't make any sense that you would do that, because the goal of the hedge is to reduce risk. And here we're going crazy, and we're actually taking on additional risk. Okay. Now, so in order to find the slope, we set this term, as I said, Q sigma delta S plus sigma delta F minus 2 rho covariance between delta S, delta F. We set this whole thing equal to 0, and we will find the optimal hedge. Okay, and it turns out with a little bit of algebra, keeping in mind, by the way, that the optimal hedge looks like this. As I explained in the notes and in class, this is what the optimal hedge looks like. Oops, I got my, it's covariance delta S, delta F, little subscripts, sigma delta F, delta F. Okay, and so remember that the optimal hedge ratio reflects the covariance between the spot and the futures divided by the variance of the futures price change. And remember what covariance is. Covariance is the correlation times the standard deviation of delta S times the standard deviation of delta F divided by the variance of delta F, which is nothing but the standard deviation twice. And so you can cross those two out. It really boils down to this formula. Now, if we plug in the optimal hedge ratio, this optimal hedge ratio, we plug that in to this formula, right? Oh, by the way, whoa boy, I overlooked this guy. Don't forget, I overlooked, and I'll put it in green, show you that I overlooked this. Don't forget there's an HS, an H squared here, and an H, oops, not a rho, an H here. It's my good thing I caught that in time. So here's the H. The H is here, and the H is there. Okay, so we want to plug in this optimal hedge ratio, this, into these H's and solve it. Okay, the math is fairly tedious. I'll cover it quickly. It's Q squared sigma delta F to the 4th power times sigma squared delta F minus 2 rho the textbook does not give you this information. They just assume you have good algebra skills and you can do it. Okay. And so all I did here was I plugged in the optimal hedge ratio for H and for H here, H squared, plugged it in. That's why I got all these square terms here, because I squared H, the optimal hedge ratio, and here it is unsquared. Okay, and keep in mind that right here, this term, this is the covariance term. See this covariance term? There it is, written out. Okay, this simplifies down to this. which boils down even further to this term. Okay, so here we are. So I simplified that math down a bit. And so if you look at my notes in the appendix on page 10 of my notes, you'll find this equation. Okay? And what does that equation say? This equation says, look, this is the variance of the cash outflow from having a spot position and a hedged position combined. The variance of that is equal to this term. The variance of the cash outflows is equal to this term. Okay. Notice if rho, what if rho was 0? You would have the variance of your cash outflow would just be the spot, because it wouldn't make any sense to hedge. And so the formula does make sense. Now, what I want to go is one step further and see, well, how much cash flow can be eliminated on a percentage basis? How much cash flow can be eliminated with the optimal hedge? Well, that calculation is 1 minus the cash flow without the hedge it's a row, okay, divided by the cash flow with the hedge, or that's with the that's with the hedge, and without the hedge is on the bottom. Okay, and so what this boils down to mathematically, this whole thing boils down to, get rid of this, it's a minus, 1 minus this whole term. What this boils down to is this equation simplifies to rho squared, believe it or not. Because it becomes, how do I get that? It's 1, I'll give you a hint, 1 minus rho squared, which equals simply rho squared. And so how much variation do you get rid of? Well, if your correlation coefficient is 0.8, then that implies you can get rid of 64% of your cash flow variation. You can get rid of and reduce your cash flow variation by 64%. If rho equals 0.90, you can get rid of 81%. And if it's 1, perfect correlation, you can get rid of 100%, right? Which matches up. Let me see if I can find the graph. Matches up with the graph I showed you earlier. Correlation of positive 1, you can get right here, and it doesn't matter if it's, since it's rho squared, if it's positive 1 or it's negative 1, you can get rid of all the variation and be right here. 0 variation at this point in your cash outflow. Okay, so that derives the math for the optimal hedge ratio and how much risk you can reduce using that optimal hedge ratio. It's a derivation. I won't even think of asking you this question on an exam, but if you're curious, there it is.